Hi, everyone. So I'm Yael Olivier. I am the optical engineer here at Run Simulation. I heads up the optical business unit. So today we are going to be talking about demystifying light and Ansys SPEOS for optical light guides. So this is basically going to be an intro to light guides and then a demo into how to create one inside of SPEOS. So as Lori said, if you have any questions, please leave them. And we'll just start getting started here. All right. So, all right, I wanted to start this with a quick overview of what is offered inside of the Ansys optical portfolio. So we have three optical softwares available. There's Ansys Lumerical, Zemax, and SPEOS. So when we're talking in this portfolio, since obviously today we will be talking about SPEOS, but I did want to cover the other two. Lumerical is where we see most photonics, everything nanoscale. Typically, and right now what's pretty big in this realm is photonic integrated circuitry. If you wanted to create a more customized diffractive element or very specific looking fibers, this is a software you would do that. And it's basically connecting the electromagnetics with light. So that's where the photonics realm plays in. Then in the center there, we have Ansys Zemax. This is our tried and true optical software, typically where we're seeing like camera designs, telescopes, microscopes, anything lens stack wise. Most people know and love Zemax for that. So moving from there into SPEOS. SPEOS is known as our system level or like environmental level light simulation software. We're also connecting mechanical with light here in SPEOS. So typically what we're seeing in SPEOS is a sort of step above Zemax in the non-sequential realm. So SPEOS is a non-sequential ray tracer, and we're able to see a lot more, especially with CAD and different light sources and human vision, but I'll get into that in just a second. So that's sort of the overall what's happening in the optical world of Ansys right now, but we are going to be talking about SPEOS today. So this is just a quick overview of like anything that SPEOS covers. SPEOS covers a wide range of different applications. It would be a very, very long webinar if I went into everything that SPEOS could do. But mostly staying on track here, it does the mechanical, like combining the CAD with light, as I was saying before, and then you're able to do a straight line analysis from there. That is also possible in Zemax, but right now it seems to be a bit easier in the CAD realm of things to keep it inside of SPEOS. The other half of this is because we have that CAD realm, we can actually make an environment surrounding whatever we're trying to simulate, which is really, really nice to do, especially when you're trying to simulate different environments or different, even let's say phases of the sun. If it was dusk or if it was noon, you'd be able to simulate that toward a camera that was also picking up another light, for example. We also have human vision available to us. So this is how the human eye would actually perceive what is being drawn up in the CAD. Now, this works perfectly with the library of materials that's available for SPEOS. So there's a wide range of materials that's not just optical materials. It also includes like paints and leather and different things like that you can actually integrate into the optical performance of what is going to happen with your light, basically, and then see how a human would see that. It gets very nitty-gritty very quickly. Another note on SPEOS is that it can live inside of SpaceClaim, NX, or Creo. It does work in all three. And it basically simulates as a CAD modeler. We'll see that in the demo. Optimization wise, it does have its own optimizer, but we can also pair it with OptiSlang. So now that I kind of went over SPEOS, we're going to go over light guides. So what is a light guide, right? When we're talking light guides, we're sometimes also using the names light pipe or light tube. If we're ever talking about fibers, it sort of falls into the light guide family. I'll talk a little bit more about that in a minute, but typically when we are defining a light guide, we have an input. It's usually an LED. At one end, we're transporting light with minimal loss, depending on your design. Sometimes you're trying to go for loss. It depends what you're trying to do there. But you're transporting the light over a length or a distance. And then you have an output face. Now your output face could be tangent to the source, which is typically what we're seeing in light guides, but in a fiber sense, it would be on the other end of that light guide or fiber. So we have an input, it transports a certain distance, and then there's an output. Now, when we're talking about like the transportation of light, I like to think of light guides or fibers as a sort of extension cord for light. I think that kind of helps, everyone understand what we're trying to do there. We're trying to extend how far the light is going with typically minimal dispersion. Obviously, it depends on what kind of design you're trying to do. So why would we use light guides? One, transportation of light, getting light from point A to point B. That's mostly what we use fibers for. So if you have fiber optic internet, for example, that's what we're seeing there is it's the transportation of light, that extension cord I was talking about. We can also reduce the amount of electronics in a system. So we're seeing this mostly like in consumer electronics or just consumer things. Like for example, we have the pictures up top, like the Nespresso machine, that there's a light guide around there, the exit sign, or even the light guides that are on the inside of that vehicle in blue, or even like a Ring doorbell, for example, with that circular blue that will indicate different colors to mean different things, or it'll blink. It's a way to communicate with the consumer. Now, previous to people really using light guides a lot, it would be a array of LEDs. So it could be up to like 12 LEDs with a sort of dispersive material on top to kind of mix the light, so you didn't just see the strict LEDs. But when we're thinking about how, it can get costly to have that many LEDs, and then on top of that, then you have to have more power, you have to pull more power, you have to cool down the system way more. Whereas here, if you design a light guide that works, you should be able to minimize your LEDs by only having to use one or two in certain systems. The other half of this as well is light uniformity. So instead of having to create like a film or a dispersive material on top of that array of LEDs, the light guide should be able to do that for you. So I think it's important to talk a little bit about the physics of light guides, just because a light guide uses total internal reflection, which I'll explain a little bit more. But this means that we are using a clear material. In this example today, we're going to be using acrylic, also known as PMMA, which is typically what we're seeing in the realm of light guides right now. We are not using mirrors at all in the system. Now, you can always add mirrors later on, but the entire point of the light guide is to use the total internal reflection, the reflection that happens at the critical angle. So I know I'm throwing a lot of words out there, but I'm going to try to break it down. So for the physics side of things, one of the biggest equations in optics that most people know about is Snell's law. This is the idea of how is your ray going to go from one material to another, and how is it going to refract? At what angle is it going to actually go through? Now, a really good example of this, and now I'm wishing I put a picture of this on here, is when you are like standing in a pool and you look down and your legs don't look like they're really connected to your body. That's because you're looking from air to then inside of water, and there's a refraction that happens there. So the angle at which the light is actually going through the water is a little bit different. Therefore, it looks different when you look down in the water. So that's sort of the idea of Snell's law. It's just calculating the refractive index change. So the material 1 is going to go into material 2. Each material has a refractive index. That refractive index just has a number to it. So we'll say here we're using PMMA at the bottom, air at the top. So in the blue, we're saying it's acrylic, and then on top in the white, it's air. So as light is going through the PMMA, once it hits the air, it's going to refract at a certain angle. Now, here this is I guess what I was just describing. If we start at an incident angle and we keep that with the first material, which in this case is going to be 1.49, we're gonna see that in just a second. That needs to be equal to the angle at which it's hitting the air, like once it goes through the air, once it refracts. That gives us our refracted transmitted angle. I hope this is making sense. So when we're talking about refraction, obviously that's not what we want for a light guide. We don't really want the light to go through. I mean, we do want the light to go through at one point. I'll get into that in just a second. But we want it to reflect first. So the whole point of this is to basically say, all right, we want a critical angle. The critical angle means that that refracted ray is going to be at 90 degrees. So if we say that that theta 2 is 90 degrees, that makes that whole sign, like the sign of 90 degrees is 1. We can then start formulating the equation to be for theta 1, which would be the critical angle. So when we reform that equation, this is the formula we get now. Now we have a critical angle formula. So to calculate the critical angle, all we're going to do is take the arc sine of 1 over 1.49, because the refractive index of air is 1 over 1.49, which is the refractive index of the PMMA. So to do that, we get the angle of 42.18 degrees. So anything above about 42.2 degrees will reflect. At the critical angle, we'll call that 0. So if it's at 42.18 degrees, it's at the critical angle. We're not going to see it reflect or refract. But if it's over 40, let's say 43 degrees, let's just be nice about it. If we say it's over 43 degrees, it's going to reflect back inward because there is a change of refractive index. If it is at, let's say, 40 degrees, so it's under the critical angle, it's going to refract. It's going to go through. It's going to go through at an angle, but it's going to go through. It's going to go from PMMA to air. This is how diamonds work. I just wanted to throw that out there. The reason why diamonds are so sparkly is because they reflect and refract light so well because of the way they're cut. Diamonds are cut on very specific angles to try to keep light inside of them as much as possible, so they're shiny and pretty, and that's why we like them. Anyway, okay, so when we're talking total internal reflection, typically that's when we're thinking, oh, so fibers, right? A lot of people understand fibers now. So I wanted to make sure we understand the differences between a fiber and a light guide. So fibers also use the physics of total internal reflection, but what we're seeing here is the light guide itself, or like the fiber itself, is smooth. So it's going from a high refractive index to a low refractive index, just how we explained in the last slide. But there's no geometry that's going on inside of that pipe. What we're doing is actually we're moving, and you can see it in that green light source, we're angling the light source itself to cause the total internal reflection going through. Whereas in a light guide now, typically the light source stays still and it's perpendicular to the guide itself. And the idea is we're going to have prisms to help create the total internal reflection, but also make sure that when the TIR ends up hitting that angle again, it's actually going to refract through. So the point of the prism is to start causing TIR, and then also when that internal reflected light hits that angle again, it's going to cause the incident angle to then be smaller than the critical angle, making it so the light is actually going to go through tangent wise through the light guide out the top. So if it's coming in from the side, it's going to go out the top. And that's sort of what we're seeing in the images below. Also to note here, it doesn't have to be a prism. It can be any shape that you want on the bottom. And this is where light guides you can make them very, very complicated if you want. And you can make them basically any shape prism on the bottom there, as long as it's sending light through the guide and then back up wherever you want the output to be. So before we get into the actual demo itself, I did want to cover a couple things because it does, when we're running through the demo, I'm going through it kind of quickly on these aspects, but I did want to touch on when we're going to define the light guide, there's a few definitions I think are really important here. So first we see the guide curve. So we're going to pick a line for the light guide to surround itself around. We'll see that in the demo. Then we need to pick a direction in which the prisms are going. So right here on the reverse direction, it's either true or false. On this here, we're going to see that I'm going to end up making it true because it's going to flip the direction of the prisms. It's either going to go in one direction or the other. We'll see that in just a second. Then for the body, we are going with circular shape here, but you can make any shape that you'd want and then have that go through. You just make a face of it. But here we're just going to stick with circular shape. Then profile diameter, we're going to keep it at 6. The optical axis, this is where you want the light to go. So the direction of the guide curve is the direction at which the prisms are going in. The optical axis is which direction do you want your light to go after it hits that prism. We'll see that in the demo as well. Then here we have a couple options for the operation. We can have hybrid, add, or remove as our options. So add is you're adding material to the bottom of the guide. Remove is you're removing material from the bottom of the guide. Or hybrid, it kind of just decides for you depending on the other inputs that you put into the definition panel. So that's kind of describing that there. Refractive index, again, I'm using PMMA, so I'm going to keep it at 1.49. Then for the distances, we're going to go curvilinear. So this just means that the distance is based on the actual curve that we are selecting. That can be changed, but I'm not going to get into all the nitty-gritty details right now. Then we also do have a start and end. This is basically the gaps that are created at the beginning and the end, because we don't need to have, a lot of times we don't need to have the prism going the entire way, especially if there's no light that needs to be seen right there. So I was explaining that. And then actually, and this is what we're going to see on the demo as well, and I might as well touch on it here. These arrows, these yellow arrows that we see them right here as well. That's going to be our indicator for this guide curve direction and our optical axis. So we see here our optical axis is going in, it looks like the X direction according to this origin here. It's going down. So we know that our light is going to come in from over here, go into this direction because we're following this arrow. So our prisms are coming in here, and then it's going to reflect off of these prisms and head out the bottom right here. So we'll see that in the demo as well. Then we also have to define the prisms themselves. So for this, we have a lot of options. I'll also talk about it in the demo, but we're sticking with our hybrid operation. So that's going to define how we're going to do things from here on out. If we're doing add or remove, there could be a little bit of differentiation that needs to happen when you're doing the definition, but that's all also listed in the user guide to follow along with. So when we're talking about step value, we're talking peak to peak. We're looking at the high point to high point of the prisms that we're looking at. Bottom trimming, I'm going to talk about constant and control points during the demo as well, but you can say it's constant, so there's no deviation between the step value. For example, that's the step value here is constant. Or we can hit control points, which is, we're saying, as if you're going so far into the light guide, if you're 50% through, then you can change it in some way, but we'll see that through the demo. It's going to make a little bit more sense that way. The trimming is how are we going to trim the guide or the prisms themselves. So you can trim from the bottom. or you can trim from the top, and you can do it through a ratio. So that will also be done. We'll see that a little bit through the control points as well. So yeah, hit on that. The next is the offset value. Now, again, we are doing hybrid operation, so it's going to be a little bit different if you do add or remove, but in the hybrid operation, it's the distance between the guide curve and the basis, the top edge of the prism, is this offset value. So basically, like, where is the top of the prism to the center line of your light guide. Then quickly, I didn't define it here because I thought it was fairly straightforward. The width value is just how wide is your prism at the bottom of your guide. Typically, you want it to be in ratio with the actual size of your guide as well. And then we have our start and end angles. So when you're creating a prism, these are probably some of the most important definitions to have available here. So your start angle is what's coming from the beginning, because where our light is going in the, I guess, to the right in this scenario here. And then our end angle is the end angle. There we go. Good job. All right. We also do have our start and end radius. We are not defining a radius of curvature on any of these prisms, but that is possible. So getting into the demo here. I think we are good on time. Yeah. All right. So let's get started. Basically, I started this demo with a CAD of an LED already ready to go, and then a spline segment. This could be a straight line if you wanted it to be a straight line, but just starting from the get, I already had something to go. Then I am also giving an origin at that LED point, just so we can understand what axis we're talking about. So in the design panel, we're going to hit the light guide option. We see it show up on the right-hand side in that design panel. We need to define which spline or which curve it's going to go on, or it could be a straight line, depending on what you want. The next thing we have to tell it is in what direction do we want our light to go. And you can see in SPEOS, it prompts you at the top there. And here, this is what I was talking about earlier. The arrows are not going in the right direction, so I'm going to flip it on that general guide curve direction. So when I do that, it's going to flip. Give it a second. There we go. It's going to flip. So now it's all in the right direction. So we know that the prisms are, the output value is going to come in that Y direction, and the prisms are going to be in like the X direction there. So going through the definition panel here, I'm going to start inputting the values that we just went over in that PowerPoint. So here I'm showing you where you can do the add, remove, or hybrid options. But I did want to touch on the main points when you have SPEOS open while this is happening in the background is you really want to have the design and simulation panel ready to go, because that's what you're going to be working with mostly, as well as that structure tree that's on the left side. I typically always set up my simulations to look similar to this, because all these panels you can move around, but you want to make sure that those are readily available, especially that definition panel, because that's where you do most of the inputs there. So here I'm just inputting all of my constant values, and then I'm going to start putting in control points for the end angle and the trimming. So here we can see that there's going to be a couple of options for doing an input. So there I'm hitting control, and we see that it pops up on the bottom there. I'm going to add a couple more points to the system. So once we add those extra points to the system, I'm going to go through and make sure that at the position percentage that we're talking about, it's right here. I think we're starting at 5%. And then there's going to be a value equated to each of those percentages. So the position percentage is if we're say like the prisms start at 10 millimeters out from the start of the light guide, it's where the prism's start is 0% and where the prism's end is 100%. Everything in between is based off percentage value. Then the value section is what is the actual defining end angle there. So it's we're going to see that happen again for that bottom trimming, for example, when I add the control points there. So the percentage is how far along the light guide we are, saying that where the prisms start, not where the light guide starts. That's where you have to pay attention to if you have a gap at the start and the end. But here again, adding a couple more lines, and then I'm going to start adding in those values. So at 25, 50, and 75% positioning, I'm going to trim off the bottom half of the light guide as we go. So at 0%, I'm trimming off 70% of the light guide. And as we go down to 100%, I'm trimming off 20. So now that everything's defined, I'm going to hit compute. And I wanted to keep the length of time inside of this demo. I'm running SPEOS here on a laptop with 8 cores. So you can see that it's still going fairly quickly. Obviously, if you had, HPC packs or even more cores just available to you on like a desktop, it would probably run a lot faster, but it's still pretty speedy here. So right here, it's creating that light guide. And we're going to see on the structure tree, it's also going to show up. So there it is on the structure tree. It created geometry. And then here, I typically like to make it a little bit transparent so we can see the prisms a bit better. And we're going to see as I zoom in here. So we see that although I went with hybrid, it added to the bottom of the light guide. And here we can see the end gap. So where those prisms end right there, that would be 100% for those control points. All right, so next we are going to start setting up a simulation. I thought this was important, especially for new users, to understand how we're going to go through this. Before I start, because this is going to start fairly quickly, we are still in the light simulation tab here in SPEOS, and we're going to move from right to left. That's typically how I like to do things. So I'm going to let this play. So we're going to hit the simulation tab as well next to that design panel, because that's where everything's going to show up for this light simulation. So we're going to start by adding some material. Anything that you're going to want to select in your like CAD-wise or geometry-wise that you want to see in your simulation, you have to add an optical material to it, even if it was already mechanically defined inside of, for example, space claim that we're seeing here. So there's a couple options you can do for the materials. Here I'm showing the optical library that is available through the download section on the customer portal. Here I was just looking at PMMA. So you'd want to take that file, put it in the same folder that your simulation is in. So then when you click library and then you want to browse for that file, it's going to be there. The other couple options that we're going to see is like opaque, or you can define an optic as well through refractive index inside of this definition panel. For the surface property for this, I'm going to not go with mirror because that defeat the entire purpose of this. I'm going to go with optical polish, which just means it's polished, it's fine. It's translucent. So I want to make sure that we hit the geometry that we're actually going to use there, and make sure you're going to hit that green check mark. Now, if your material is not actually defined, you can kind of see it in that material section in the simulation panel. When it's purple or blue, whatever color you're seeing on the screen there, that means it's actually defined. If it was gray, it's not fully defined, and then it'll throw an error for you when you try to simulate it. So here I was just selecting the LED body to be opaque, so solid, and I'm giving it a small reflectance of 10%. Then we're going to add in our source. So I'm going to, add in an LED here. So for the source options, I'm going to select a spectrum again from the optical library, and all these are in the library currently. So from that library, I can pick a spectrum file. I'm going to end up picking the white LED file from that spectrum library. So I'm going to leave the intensity as Lambertian and 180. The only thing I'm going to change here is changing the luminous flux to 200 lumens. You can also select to do your source in watts if that's what you're used to using. Then I want to select a surface. So I'm going to hide the light guide and I'm going to select the surfaces of that LED. Again, hit that green check mark. And we see that it looks like an explosion happened. So what I'm going to do is I'm going to go into the options of that definition panel and take down the number of rays and also how long the rays are, just so we can get an idea of where our light is going and making sure that's going in the right direction. Something to note here, this is just for visualization purposes of like understanding where your source is. It's when you define the number of rays in that option panel, it doesn't affect your simulation number of rays. Then what we're going to do is we're going to add a sensor. So I'm going to go with the radiant sensor here. So I don't know, when I clicked radiant sensor, I didn't know where it stuck to. It's always going to look for an origin. And here it selected the original origin of the system, but I wanted to go to the other one that I had set up on the other side of the light guide. So all you need to do is just click on that origin when you're defining the sensor. And then of course it's facing the wrong direction. So we're going to try to make sure we're checking our axis system and making sure that we're on the right axis. So here I'm going to define the y-axis as what is actually the z-axis on that origin. And as I'm flipping this around, it's now flipped the wrong way. So all I need to do is go into that X direction and press true for the reverse direction. So now we have our radiant sensor set up. I'm going to hit that blue square in the corner and we can see what the sensor is actually going to see. So this is a good cross check to make sure that like what you're trying to simulate is actually going to show up in the square that you're going to simulate it in. When you have it in this mode, this is probably the best time to do the X and Y dimensions of the sensor itself. It doesn't need to be huge. I'm not doing a huge light guide here. So I am flipping the mirror extent to true, which just means that in both the X and Y direction, it's gonna fit. I'm doing that for both the X and Y dimensions. And I'm also hiking up the sampling, which is going to make it a finer resolution. So you can either adjust the number on resolution or the number on sampling, but they correlate with each other. As you can see, they update once one of them updates. So now that I'm happy with that, there's also the options if you wanted to see the grid of your pixel, basically your pixel grid, you can do that as well. I am also going to set this to layer for source. This is helpful later on for like post-processing. If you have multiple sources, you can define it to only see one source at a time. For the type, I'm going to go with colorimetric because I'm just trying to see what it's going to look like. I'm not really too worried about the other analyses that need to be done. When I hit colorimetric, the wavelength options did show up. I'm going to leave them as is, as the visible spectrum. And then from here, we are going to hit back in the light simulation tab, go to a direct simulation. All right. So once we have our direct simulation ready to go, we need to just set that guy up. That's going to be in the next video here. I know we're like sort of running out of time. I should have 7 more minutes. But okay, so now that we're ready for our direct simulation to go, I'm just going to play it here and just keep talking through it. Let's go. Oh, buddy, hold on. It is not playing the video. There it is. Okay. All right. So light simulation tab. We're going to do a direct simulation. So here we want to make sure we're going to hit all the geometries that we need. And again, in that top left corner, it's going to tell you what it needs. So you just keep clicking along. We're just saying that we want everything in there. So source, sensor, geometries, and then we can, before we hit compute, actually, we're going to do a light path expert on this. And we're also going to hike up the number of rays we're sending through the system. So now we're going to send 2 million rays through the system. The stop conditions, that's where you want to do it. Again, when you mess with the source rays, it doesn't really matter. What does matter is when you're actually sending those rays inside of the direct simulation. So as this is processing, again, I'm showing you real time with 8 cores, how long this is taking. So while that's happening, I'm going to talk about the light expert really quick. So I set light expert to true, and then I also set the sensor at the bottom underneath the definition panel. The LXP is checked marked on that sensor for the radiance sensor there. Now this means we're going to be able to ray trace, basically back ray trace what's going to happen in the system. So we'll see that a little bit better once the simulation is done running, but that's super helpful, especially if we're looking at stray light or just trying to figure out where the heck is our light coming from, where is it bouncing. Typically the light expert is really, really handy. So now our simulation is done. We can see that it popped up on our sensor inside of the actual simulation window, but I'm going to pull out the XMP file here. So this is like an image of what that sensor is seeing. Here we have a couple of options. So we can go to the measures window. This is typically, it just pops up with like a little square. You can do points. You can also do different shapes here to define the area that you're looking at. Then you can use different measurement tools. So you can say like, oh, I want total flux, RMS contrast. So like if you want uniformity, you'd go with RMS contrast. If you want to look at the color that you're seeing inside of the simulation, you have those tools as well. There's a lot of little hidden tools inside of SPEOS that are, it's good to know about there. So then I'm going to open up the LPF file, which looks exactly the same as the XMP, except now that square that we have is actually going to show the ray trace. So while I was doing this, I hit a couple of keys and you're going to see the ray trace kind of goes out of sorts. Yeah. We're going to bring it back. We're going to go back to the sketch panel and bring it back to center there. And there we have a better idea as to where that light is coming from. So all of the light that's on inside of that square on that LPF file, we can see how it's getting ray traced through the system from the source. So we can see as we move that square along, so the rays are going to follow it. Now, if I made that box really big and I made the entire light guide inside of that box, you would see the output rays coming out all along the entire length. I'm just keeping the box small for this purpose. You are also able to change the ray numbers. There are a lot of rays being shot through the system right now. You can pare that down to just a few numbers, or like the ray length on there as well. So I think that's it for that guy. So that's what I was saying right here in this section, this ray number and ray length, that's just for your imaging purposes, just like how that source was. It doesn't have an actual impact on the simulation itself because it's still shooting through 2 million rays. But if you wanted to get a better idea of what was going on and not have an entire mess in here, you can pare these down. So in the end, the idea is to, if we had a second light guide here, this would be like the halo effect on the outside of a headlight. That's basically the idea here. When we're seeing it in full context, we see that there's a bunch of points defined along this XMP file that is matching up with the measures window inside of this simulation. So on these parameters. So these parameters here are defined as these little points. And then right here, we're going for RMS contrast. We're also looking at the average, minimum, and maximum of the system, so along these points. So we're measuring along this and making sure that we're trying to get as uniform, so RMS contrast is saying uniform, as uniform as possible. Now, all of these parameters, and especially the light guide parameters that we define, like the prisms and all of that, that's all able to be optimized. So this would be like the setup for like right before you're about to do the optimization. And then when you're ready for it, you can throw all these parameters into a system like OptiSlang and do like a sensitivity analysis. You can do tolerance analysis, and you can also just do a regular optimization. So that is that. Lori, I'll hand it back to you.